Okay, here we go. So my name's Jamie McCutcheon. I am the principal and founder of Rymar Waterworks. Appreciate everybody joining us this morning for a webinar on Skimmer Basin Design. Like I said, I am a 92 grad of Clemson University with a bachelor in civil engineering. Founded CCAD Engineering, which is a small civil engineering company in 1999 that I owned until 2018. I invented the Marley float skimmer back in 2013. And I am a licensed engineer, South Carolina, North Carolina, and Georgia. Let's give you that introduction just to let you know that for most of you, I've done similar work to what you've done for almost 30 years now, and hopefully today is going to be a very technical presentation that you will learn about. Um, I do appreciate everybody staying muted during the presentation, but if you do have a question, feel free to unmute or use the chat. Lynn Ramsey is our sales director. She's on here as our co-host. She'll be monitoring the chat as well. So I'm also going to cut my camera off. It just helps with the recording later. So, all right. So today's agenda, we're going to do a introduction to skimmers or floating outlets, as they're called in some places. We're going to go over basics of skimmer basin design. We have the focus today on Indiana, Texas, and Ohio. Each month we do these. We try to change up the states that we kind of focus on. So this month we're focusing on those three. Then we're going to do a little pivot and talk about using skimmers for post-construction, why you would want to do that. We'll get into how you would model a skimmer and hydroflow. Um, and then we're going to wrap up with our water quality filter and a filtration-based design, which is a pretty new concept we just want to introduce to you that we're starting to get out. So as we get started here, I want to do one quick poll, and so we'll launch that. And just like to know for our crew today, how familiar are you with skimmers? So everyone can answer that quickly. Appreciate everybody jumping in and doing that. Um, looks like we've got a good mix of new to somewhat and a handful that are very familiar. So in that, share that real quick. So it looks like about 50%, well, about 80, almost 85% of you are either new to it or somewhat new. So hopefully we're going to give you some good information today. So, previously before skimmers, we typically had a riser structure as either perforated or maybe had a hole at the bottom. Often had some sort of, riprap or stone check dam in front of it to provide some silt protection. But you can see in this basin, the idea is this basin is pulling water or discharging water from the bottom of the basin where we're trying to collect all the sediment. So skimmers have been around now for, I guess, about 20 to 25 years. The idea is that they float. They withdraw water from near the surface or just below the surface and drain the basin from the top down. This allows a couple of things. One, you're releasing the cleaner water higher in the water column, and you're giving the sediment more time to settle down to the bottom, and releasing the water that's not directly on the bottom. Skimmers have been shown to be very effective. Typically, it's fairly easy to achieve at least 80% trapping efficiency with a basin in a properly designed with a properly designed skimmer. So there are a number of skimmers on the market. You've got the Faircloth skimmer. They were kind of the first to market about 25 years ago. The erosion supply skimmer, or ESC, is kind of similar to the Faircloth. You have the IAS skimmer, which is kind of a T design, and then you have the Marley float, which actually looks a little bit different than the others. So this is a little quick video. This is a sediment basin on a site that has about 8 acres disturbed, draining to it. This is a major storm. It actually washed out part of the bank, but had really, muddy water in the basin. Here's the discharge. You can see there, it's really clear water, much clearer than you would probably think would be discharged from that basin. Really important here, this site was about 100 yards from a lake. And so we really didn't want to get complaints from the neighbors about turning the lake brown. So anyway, the skimmer was working really well. Um, got to go really quickly here, the 3 fundamentals of sediment basin design. So number one is going to be basin volume. So the basin volume is based on the area flowing to the basin. Regulations differ from state to state, whether that's total area or disturbed area to be used in your calculations. What we see in most cases is, a range of 1,800 or 3,600 cubic feet per acre flow into the basin. Some have other standards than that. Indiana being one is 5,600 cubic feet, but 1,800 and 3,600 are the most common. So, for example, if you had 5 acres at 3,600 cubic feet required, you'd have an 18,000 cubic foot required volume. Some areas, Ohio, Indiana, and Texas, coincidentally, all require the basins to have a permanent pool volume or sediment storage volume that is not drained by the skimmer. And you do not include that volume when you're sizing your skimmer. The most important thing about this is use the required volume, not your actual volume to size the skimmer. That's really important, especially if that basin is going to be a future detention pond, and that basin may have anywhere 3 times, 5 times. I've seen some even 10 times the volume required for sediment storage as the actual volume. And if you size the skimmer based on actual, you're going to drain that required volume too fast and not meet your regs. So number two is going to be dewatering time. So again, sediment basins are the principle is they work by allowing time for sediment to settle to the bottom. Again, we're releasing that cleaner water from the surface using the skimmer. That time is going to vary depending on your soil type, right? If you've got a sandy soil, it's going to settle much quicker. Silts and clay is going to take much longer. What we see is the most common standard is 2 to 5 days. A lot of areas recommend trying to hit a 3-day target. Note that your engineering judgment is going to need to balance the need for extended times for your soil types versus the frequency for rain events. So if you're in an area that experiences, if you're in the southeast and you're getting those every afternoon thunderstorms, you probably need to have that basin drain down faster than 5 days, right? Probably needs to be a 2 to 5 day time frame so you've got volume ready for the next storm event. And then the third one is simply the flow rate. And so once you know your basin volume and your dewatering time, very simple to establish your flow rate. Just simply basin volume divided by dewatering time is going to be your flow rate. And you'll use the minimum dewatering time to determine your max flow rate and maximum time to determine the minimum flow rate. Once that range is determined, you can select the appropriate skimmer based on the manufacturer specification. So in our example, we had 18,000 cubic feet. If you drain it in 2 days, you're going to pick a skimmer that has a max flow rate of around 9,000 cubic feet per day. If you go out to 5 days, that'd be 3,600 cubic feet per day. So a pretty big range of flow. Note that if you do a lower flow rate, it'll often result in maybe a smaller and typically less expensive skimmer. However, that's kind of a secondary requirement. So another quick poll here, just like to know where our folks are today that have joined us. So if you could answer where you're participating from today. Looks like Ohio's leading the way with South Carolina, Georgia, Indiana, and a few Texas as well. So in that poll, share the results. So yeah, Ohio, we got about 10 people there. 3 from South Carolina, Georgia, Indiana, and Texas, and a few others as well. All right. I appreciate it. I'm not gonna reply. We'll get a little thing going in the chat. Y'all have fun with that.
Is that editorial, sir, or mistake or typo mistake? You said for 1,800 for one day it is almost 9,000 cubic feet, and on the 5 days should be 45, not 35. That I'm reading.
I would be 3,600. Yeah, 3,600.
But if it's 5 days, it will be now. First day is 9,000. The 5 days should be 9 times 5, 45, not 36. Is that right?
Yeah, I think so.
So it should be, the number is incorrect.
Yeah, I'll correct that. So,
all right, thank you.
So Indiana, let's talk about Indiana standards here first. So in Indiana, you're going to have a dewatering zone volume of 5,600 cubic feet per acre, or you can calculate it as your 1 year, 24-hour storm. Now, depending on your area in Indiana and rainfall, you're probably going to be a smaller volume. by calculating that. So probably worth the time to go through and calculate your 24-hour storm, 1 year 24-hour storm volume for that, or use the 5,600 cubic feet per acre. In addition to that, you're going to have 1,000 cubic feet per disturbed acre for sediment storage that is below the inlet of the skimmer. So that is going to be like a permanent pool in your basin to allow for accumulation of sediment. So again, in the written 5,600 cubic feet, or calculate it for the 1 year 24-hour storm. Dewatering zone, they want to drain that in no less than 48 hours or 2 days, and no longer than 72 hours after a runoff event. So, 2 to 3 day time frame. That's a tighter window than what we see in a lot of areas, but that's what Indiana has decided to use. They do say withdraw from the surface of the water column and they call it a floating outlet versus a skimmer. And you do, if you're in Indiana or other areas that experience extended freezing time periods, we do recommend that you install a perforated riser with a valve, so just a pipe out of your outlet structure with a riser on it, so that if you do need to dewater and you've got, a foot of ice or so at the top of the basin, that skimmer is obviously going to be frozen and not functioning well. So for folks in Ohio, Indiana, other places that get some significant freezing, we do recommend that. And then again, you've got 1,000 cubic feet per acre of disturbed area for your sediment zone. And again, they say this should not be included in your dewatering storage volume when you're calculating the size of the skimmer. So again, got the worksheet here, put that same information in there. They want to see the total watershed and disturbed. The total goes with dewatering volume, disturbed goes with sediment storage. And then that dewatering time, 48 to 72 hours. And we recommend that you put in that range of time when you're specifying the skimmer. That way, if a contractor wants to use a different skimmer, it's easier to hit a range of time than hit a very precise time, because all skimmers don't always flow the same. So again, this is just the IDEM standards that are out there. Just give me one too fast there for sediment traps and basins. These have draft on it. I need to update that. They're now been, they're not draft anymore. These are actually the current Indiana standards. So, and those of you that are in Indiana, we are going to be doing a couple of events in Indiana coming up over the next couple of months. We got, I guess, 2 or 3 events. We'll be there. So hopefully we can see a few of you at some of those. All right, Texas sediment basin standards. So in Texas, TCEQ has put out that you must provide sufficient storage to contain a calculated volume of a 2-year 24-hour storm. Remember, Indiana was a 1-year 24-hour storm, so you can calculate the 2-year storm, or if you don't calculate it, use at least 3,600 cubic feet of storage per acre drain. So that'd be total area, not disturbed area. And then they do have this, unless infeasible, when discharging from sediment basins, use structures that withdraw from the surface, i.e. a skimmer. Again, the infeasible portion is pretty rare unless you're experiencing frozen conditions. Again, here's the north central Texas is what this comes from, a different manual than TCEQ. Again, they want to use the manufacturer's flow rate when you select the discharge rate for the skimmer. Again, minimum design dewatering time of 36 hours and draining no less than 72. So very similar to what Indiana has. And the primary outlet you want to handle for the 25-year 24-hour storm. So the primary outlet would be the skimmer plus the riser structure. Again, got that unless infeasible, withdraw from the surface. And then, discharge rate for skimmers are dependent on the orifice configuration. So one important thing is skimmers don't all flow the same. We'll talk about that in a few minutes. So make sure you're using whatever the manufacturer recommends there. Same little worksheet here. Got your total area, disturbed area, minimum required volume on that. So then also Ohio, I know we had some Ohio folks on today. Ohio EPA has some good information on their website, and they actually have a dewatering compliance tool that you can use. So again, they have a minimum sediment storage volume of 1,000 cubic feet per disturbed acre. That's very similar to the Indiana standard. Minimum dewatering volume is 1,800 cubic feet per drainage acre. If you're in certain watersheds, that Big Darby Creek watershed, it goes up 3,600 cubic feet. And detention time or dewatering time is 48 to 160 hours, so 2 to 7 days, so much bigger range of time in Indiana. They have this little tool that you can use, so you can put all that information in, put in here the total area and disturbed area. It'll tell you the volume you need for both of those portions of your basin. When you build in your basin, you build up that volume and you've got your dewatering zone and your sediment storage zone. And then I do want to point out that the Marley float is included in the Ohio EPA design tool. They have several different skimmers there, but since this is our webinar, we like to point that out that the Marley is one of the selected standards there. And we work very closely with Ohio EPA on developing our own design tool, which mimics the Ohio design tool very closely. So just kind of quick summary, since we're talking about Indiana, Texas, Ohio today, just see how they vary. Basin volume, anywhere from 5,600 cubic feet to 36 to 1,800. So big difference there in what your basin volume would be. Again, that's just what the states have decided. All three of these require 1,000 cubic foot sediment storage. I don't have that in Texas, but they require that. Surface area, some states have a formula for this. These don't specify. Ohio has a max depth of 5 feet. Indiana says preferred depth of 3 feet. Texas just has a length to width ratio to meet. The principal spillway, the design of that's anywhere from 2 to 10-year storm. Emergency spillways, 25-year storm. Sediment basins, some places say any sediment basin has to have it. Others have a 10 acres or more has to have a skimmer. And then dewatering time, again, 48 to 72, 36 to 72, and 2 to 7. So point here is that pay attention to your state standards. They do vary quite widely from state to state. We talked about skimmer flows. So this is, skimmers are often thought of as constant head, constant flow devices. And so that's not really true. This is a chart that TRI Environmental did when they did a study for Georgia. And for example, here they tested 3 different 3-inch skimmers. So they had a type 2, a type 1, and type 3. Their test tank is 4 feet deep. So they go from 1 foot here to 4 feet depths. And if you look at these at 1 foot of depth, 2 of the skimmers were very close, around 37 GPM, and one was nearly double at 70 GPM. All 3 skimmers had about a 25% increase in flow rate. And at 4 foot depth, the 2 here were again pretty close, about 50 GPM, but the other one again is nearly double at 90 GPM. So the point being that if you simply specify a 3-inch skimmer and you don't give any more information to that on your plans, you may get one of these that flows, maybe you intended to have the lower flow rate. You may get the higher flow rate that drains the pond too fast, or vice versa. You may intended to do the higher flow rate and get a skimmer that drains, at half the time and you're taking too long. So important on your plans to identify the volume you're draining and the time frame and flow rate that you're draining so that the contractors can select a skimmer that meets those requirements. Again, I mentioned we have a design tool. So we have 2 different versions of this. This one is just for a dry pond. We have another one that is designed for a wet pond that includes the calculation for the sediment storage area. But they work very similar. So you got room here to put in your date, project name, location, company name, engineer, put in your sediment basin description. We have 2 lines for other. Sometimes the sediment basin may change in phase 1 to phase 2. And so you can put some notes in here. One key thing here is this little box. So we've created this little check because what reviewers have told us, and I know we have a few MS4 folks on today, what reviewers have told us is that the biggest mistake they see from engineers when they're designing a skimmer basin is that they use the provided volume, which often is much larger than required, which we talked about. So this is the check. Put in your area to the basin and whatever your required cubic foot is for your area, and that'll calculate that required volume for you. So over here, you've got a little input box for the tool. So we've got our minimum max time to drain. So it's by default set to 2 to 5 days. But if you're in Texas or Indiana, need to change that to that 36 or 48 to 72 hours. Pond depth. Now the pond depth is just the depth required to meet your required volume. If your sediment basin's 6 feet deep, don't put in 6 here. If you can meet your required volume at 3, and you got a top length and width and a bottom length and width. Now, I've seen very few perfectly square or rectangular basins, so you want to use your engineering judgment and manipulate these numbers so that the calculated pond volume is close to your required. We recommend to get within about 5% plus or minus. Again, you're trying to meet a range typically of at least 24 hours to maybe 72-hour range. And so you don't have to spend all day, extra time getting this to exactly match that up. And then when you do that, what's that, Missouri?
No.
Okay. So when you do that, our tool will calculate the flow rate for each one of our basins. And then each one of our skimmers, excuse me, at the bottom, there's a skimmer report page tab. When you click that report page tab, it'll take you to the next sheet, which is a nice, neat 8.5 by 11. The top is going to have all your information you entered. So it's going to have everything you put in, calculated volume. It's going to identify the minimum flow rate for the maximum time and the maximum flow rate for the minimum time. So in this case, we got a range of 0.032 CFS to 0.08, or basically just under 3,000 cubic feet to just under 7,000 cubic feet per day. And then because it's our tool, we're going to give you the drawdown time for every one of our skimmers with each orifice configuration, and whatever range of time you set is going to tell you that which skimmers meet that range. So in this case, we typically try to shoot for that 3-day time frame, just the general. So we would probably recommend to go with a 2-inch skimmer with a 2-inch orifice to drain in 69 hours. If you want to drain it as fast as possible, you can go up to the 4-inch skimmer with a 2-inch orifice, drain it in 48 hours. So that'll calculate that for you. One thing I didn't say about our tool, I'm gonna back up. The tool here takes this pond depth and it breaks that depth down in increments, about 20 different increments there. And we calculate the flow rate through each increment to take into fact that flow rate curve on each skimmer. So this isn't just a orifice equation, standard flow rate. It factors in that flow rate curve to more accurately give you that drain time for the basin. So it factors that in. So just want to point that out. We do have details available on our website. So we call it our engineer's pack. It's a zip file that'll download our skimmer details and these basin details. The basin details, there's 4 of them included. So this one is for which would probably be a temporary basin. So it doesn't have a riser structure, just a barrel going out. This would be a dry basin. Then it has, maybe you have a riser structure. And in this case, you've got a permanent pool. So for what we're focused on today, Texas, Indiana, and Ohio, you'd have this permanent pool volume. So over here, you're going to have your general basin design criteria for your site. So this one's going to apply to all the basins on site. You may have a minimum length to width ratio or maximum length to width ratio that may not apply in some areas. You're going to have sediment storage volume. Again, that's typically 1,000 cubic feet per disturbed acre. Dewatering volume. This one is 1,800 cubic feet per acre, but you can edit that. These are available in CAD, to change that to 3,600 or 5,600. Surface area required may not be applicable. Here's where you set your range of time. So in this case, I've set it at 48 to 120 hours. And then down here, you've got your information. So you've got your sediment storage. Again, here, you just want to make sure your provided meets your required. Your dewatering volume, again, if you've got a riser, this is going to be a permanent pond. Your provided is probably going to be much higher than required. You're going to have the drainage area, disturbed area, your Q flow rate that you're basing your storm on, either your 2 or 10-year storm, whatever's required in your area, basin surface area. And here's just a standard basin information: bottom of the basin elevation, outlet invert information, riser, a barrel pipe size, the top of your riser, emergency spillway, elevation, width, and then here you get to your skimmer information. So your skimmer size, skimmer orifice diameter, the skimmer type. It is our tools. We filled in Marley for you. Is an equal allowed, yes or no? Now, most of the time you're going to have check yes there. And we know that in most cases, approved equals are a good standard to have available for your contractors. There may be some situations where you don't want to allow equals, and we'll get into that a little later. And then here you set your minimum and maximum flow rate for that basin based on the time frame that you're allowed over here. So, based on these min and maxes, you're going to come up with that flow rate. Again, our tool gives you that information to easily plug into your detail. This is our standard skimmer detail. So just a couple of things about it. All of our skimmers come with a standard orifice plate. So some other skimmers out there have a little disc that you cut to meet a size. Ours don't do that. We just have standard orifices. All of these orifices have been third-party tested. This little chart up here is the flow rates for each orifice configuration. The most common question we get is what length pipe do we need here? What we recommend is 1.4 times the height of your riser structure. What that does is allows this to get on like about a 45-degree angle, which is nice for the, for the flow rate of the skimmer, if it hits the max height. And so typically the only time we see clogging or main time we see any kind of clogging issues with the skimmer is if water comes over it. So if the pipe, say if this pipe was 3 feet and our riser's 6 feet, and water gets up, well, water's coming over the top of the skimmer because the skimmer can't rise that much. A couple of quick pictures here. This is a really good example of a dry sediment basin. Obviously just been installed. They tracked in the size. They've got their baffle in. There's probably a couple more baffles in the basin here. One thing I like to point out about this picture is this stone pad. We recommend that there's be a little depression here. That way the skimmer sits down as far as possible, because the way this is set up, there's going to be 6 to 8 inches of water that can't get out of the skimmer because the skimmer's above it. And so if you're really trying to do a dry basin, you want to do that. Now, the states we talked about today have a permanent pool in here, so that really doesn't apply. So you're going to have an undercut here, and your skimmer's going to sit down. Skimmers are all gravity flow, so once they hit that invert elevation, they're going to stop flowing. And it'll take either evaporation or an infiltration for the rest of the water to drain out. This is probably the worst install I've ever seen. This was inspector sent us these photos. I don't even know how they attached it here to the valve, but it's attached somehow. It's about 6 inches of pipe. Got our skimmer sitting out there. They got the valve open on this side, so all the water's going around anyway. We had seen some contractors install this upside down. Now, this is really difficult to do because there's a label on top that says this side up and actually has a QR code to go to an installation video to help them install it correctly, but it does happen. Good news is they only put 6 inches of pipe here, so this skimmer can't float up very high, so the pond's still going to drain down over time, but it's not functioning correctly, obviously. And then this one, skimmers are not maintenance free. This is another brand of skimmer that has a root ball, in it. They had vegetation growing up out through the intake, and so this pond wouldn't ever drain because no water could get in the skimmer because it was clogged by the vegetation. You can see the mud here. It also needs to be cleaned out, but anyway, not a good job of maintenance in this case by the contractor. All right, so that ends kind of the basic design information. Does anybody have any questions, or if they want to put anything in the chat, I'll be happy to answer. Hey, and Lynn, you might want to mention the March 19th event too in Indiana, since we've got a good Indiana group on here. All right, so we're going to move into permanent use. Okay, we're going to move into permanent use of skimmers. So we got one more poll. Launch this for you and say, have you ever considered a skimmer for permanent use? All right, looks like we actually have one yes, which I always get a little excited. We actually have a yes or two. That means hopefully our word's getting out. Majority no. I actually got a good percentage that say they've considered it. So I'm glad to know you're at least thinking about it as well. And those of you who say no, hopefully this next little portion will give you something to consider. So, I'm going to focus on a dry basin. Now, if you have a wet basin, this is going to be a little bit different. But dry basins seem to be the most common stormwater BMP used. So a typical dry basin, when you finish construction, you're going to remove the skimmer. You're going to install some sort of low flow orifice here at the bottom, and that's going to be designed to release your first flush, water quality volume. And then you're going to put in some sort of guard or filter to reduce clogging, right? Because depending on the size of your site, this orifice down at the bottom may be 2 inches or 3 inches. I've seen some as small as 1 inch, which obviously is going to clog really quick. Now, the other thing about this is the whole point of the pond and that first flush is to hold the water in the pond long enough for whatever sediment pollutants to settle out and come to the bottom of the pond. Well, now we're discharging from the bottom of the pond where that sediment pollutant load is the highest. So, just like during construction, we're using skimmers. It kind of makes sense to use skimmers for post-construction. Again, basins are relying on that settlement, natural settling of sediment particles as they travel from the inlet to the outlet. The skimmers release that cleaner water from the surface. Again, widely accepted for construction and proven to be very cost effective. So just kind of common sense says, hey, if it really works out great in construction, wouldn't it make sense to at least consider using it for post-construction to help us with water quality? So a little case study on that. This is our site that we use kind of as our R&D facility unofficially, but this pond had been neglected for about 20 years. You see all this junk and debris in it. Well, it actually looks better now. We actually had to go in and cut timber out of this pond, 6 and 8 inch trees, and the change that slide up. But we got the county once we got it all cut. We found out there's a 2 inch orifice 6 feet below what's now the bottom of the pond. So imagine you got all this muck and debris. It's built up about 6 feet in this pond, and I had a 2 inch orifice down there. That was the low flow orifice. So we redesigned the pond. We filled in the old orifices. We put in new ones here. And instead of going back with a 2 inch orifice here, we installed a skimmer with a 5 inch orifice. Our 5 inch orifice with very little head had a similar flow rate to that 2 inch orifice with say 3, 4, or 5 feet of head on it. So we were able to maintain the flow rate for our water quality volume using the skimmer, but do so in an area with a way that's going to be much better for maintenance. So this was actually the first skimmer that had been approved in this county for permanent use. So they required us to monitor it monthly for the first 12 months to make sure it's working properly. And it was. These are pictures from those first 12 months to show it's really doing a good job. Then about a year or so after it was installed, the owners of the pond decided to do some maintenance, and they were cutting all the vegetation on the side of the ponds. And the pond has really steep sides, so it's about 1.5 to 1 slopes, about 3/4 of an acre big. Well, the landscapers cut everything, let it fall to the bottom, and before they could get it raked up and get it out, we had a 5 inch rain in just a few hours and washed all that debris down here in the bottom. Okay, but you can see the skimmer sitting here amongst all that junk did drain the pond down, and even if it had clogged, it'd be much easier to get to. But if you can imagine, if this was a 2 inch orifice, it's hard to tell from this picture, but these are 6 foot riser sections. So these orifices up here are about 8, 9 feet above the bottom of the pond. So if you had to try to get to this with 9 feet of water in this pond, it would be extremely difficult and hazardous to do so. So having the skimmer there makes it much easier to get to. We just cleaned this out, so I hadn't put the rope back, but typically you'd have a rope attached here, so you can just pull the skimmer to the side, make it really easy to get it unclogged if it does clog up. Much easier than getting down to a 2 inch orifice. So if you're going to consider skimmers for post-construction, you've got to be able to model them correctly in the hydrology software in order to get your pre and post calculations done and your water quality calculations done, correct? So HydroFlow seems to be the most common software we use now. HydroCAD's out there, ICPR, XP Swim, there's a few others, but hopefully if you don't use HydroFlow, this example will kind of give you the idea on how to apply it to other software as well. So this is a site I actually worked on many, many years ago, and it was in the city of Greenville. And city of Greenville is a little unique, and they require quantity control during construction. So we had to run HydroFlow with our skimmer anyway to show we're meeting our quantity control. So we had a site that's about 5.5 acres. This 3.4 up here was not being disturbed, and this 2.25 down here was, and this goes to this little sediment basin and then discharges down to a road. So our pre-development, we had again 5.5 acres, curve number 59, time of concentration was 18.5 minutes. Post-development, the portion disturbed, 2.25, again, curve number 86, that's a bare earth disturbed condition, time of concentration down to 7 minutes. And then here, a couple of things with hydroflow. When you're building your basin, you want to put in your stage, elevation and area. You want to put in stages so that you can enter the data from the skimmer detail for the flow rate. So in this case, we enter stages 0, 0.1, 0.3, 0.5, and every half a foot. Our detail over here, gives you the flow rate for the skimmer, 0.1, 0.3, 0.5, and every half a foot up to 4 feet. Now, this basin just happened to be 4 feet deep, so that worked out fine. But we had here, when we built an outlet structure, we had a outlet pipe, 18-inch pipe going out. It's a pretty complicated structure for a small pond. It had a 6-inch orifice, 1.75 feet above the bottom of the pond. Had our riser structure. Riser structure had a rectangular weir in the top of the riser. And then here's kind of the secret sauce to this is user defined column. This is where you plug in your skimmer flow rate. So you just translate from the detail in here. At each stage we set up, you put in that user defined, and that creates that flow rate curve for the skimmer to factor into your hydrology. Now, what happens if your pond's over 4 feet deep? Well, you've got a couple of different options in that case. If it's not much over 4 feet deep, you can just maintain that flow rate at 4 feet. Flow rates tend to flatten out around that, so they're not going up a lot. This is going up, a hundredth, so not a big increase in flow. Not going to make a big change. Let's say it's 8 or 10 feet deep. In that case, what you'd want to do is go back and use our tool. You set your pond depth here at 8 feet. And again, it'll break that 8 feet up into 20 different flow rate increments, and it'll give you the flow rate at each increment. Now, this example's, maybe I need to change that up. This is our 2-inch with a 1/2 inch orifice. So this thing flows at a trickle. You only got 4/1000ths of a CFS coming out. So it's not seeing much change. But the bigger skimmers, you're going to see more of a flow rate change over that depth. And so you can use whatever depth of your pond and then break that up and then use those increments to factor in the flow. Just get something close to the nearest foot or half a foot and plug it in. So that'll help you build that flow rate curve. So if you put that here and there. Now, if you go back to hydroflow and look at your outlet structure in a schematic, you got your riser structure, we got our 6-inch orifice, we got our rectangular weir. Normally you'd have a low flow orifice down here at the bottom, right? That would be your outlet. In this case, you don't have that because you've got your user defined. It doesn't show that in the schematic. But when you look at your stage discharge curve, this is your skimmer flow here till you hit that first orifice, then you hit the weir, then you hit the top of the riser, and it goes on out. So that's the quick version on hydroflow. We'll talk about a second. We have a little more advanced, a more detailed study of that on our website. So last thing we'll get into here, actually next to last thing, I got one little add on the end here for you. But this is advanced skimmer modeling for filtration-based water quality. So our newest product is a filter that goes around the skimmer, and it's intended to utilize to provide post-construction water quality. So it's got an outer filter that's like a polyethylene fabric. Basically, it's a Mirify kind of fabric. It's basically just a screen. Okay, so we're screening out all the big stuff, with that. The inner fabric here is a non-woven called Absorbit. It absorbs hydrocarbons. It'll help some with metals, has some other benefits. And the idea is that we're using our skimmer to pull the water in the top 3 feet, because all these filters hang down about 3 feet, pull the water through the filters to clean them and go to the skimmer. Now, the filter is open at the bottom, so we're also using some gravity in this as well. So once the water gets below 3 feet below the skimmer, it can come up, but there's not enough force in that water flow to pull the sediment particle up with it. So we're just allowing gravity to do its job below 3 feet and letting the filter do the job in the top 3 feet. So we also have some R&D underway. We're going to be looking at ways to do metals, hydrocarbons, and other pollutants. This goes back to that same pond I mentioned, earlier. That's kind of our R&D spot. This was our prototype. So we had our filter out there. What you can see is we had a screen. This is basically a turbidity curtain we used as a prototype with a screen in it, and that's our absorbent. You can see here, you can't see it well, but there's slits in this fabric. This is actually 2 layers of fabric, and they have slits in them. So they have 6-inch panels. The panels are all set 3 inches. And the idea is to create water kind of weaving through that material. And it allows more contact time with the material to help grab those sediment particles, as well as some of the other pollutants in there. This is a pretty good photo, again, the prototype, but you can see the turbidity in the pond outside the filter is much higher than the turbidity as it gets close to the skimmer. And then this is actually the outlet of the pond. Pretty clean water. I definitely wouldn't drink it, but we can tell that this system, filter and skimmer, is doing a really good job of releasing very, very clean water considering what's coming in the pond. So once we prototyped this for about 2 years and felt like we had a good system, we had it third-party tested, and that testing confirmed over 90% TSS removal with this system. Now, that testing was done by TRI Environmental. They tested 2 versions of the skimmer, and many of you may not be aware, but ASTM now has standards for sediment retention devices. So the standard we used was the C1746. So it sets the protocol for doing all the testing for this. One other thing we did when we did our testing is we wanted to figure out what the benefit of the filter and the skimmer was, regardless of the pond design. So most ponds are going to have a forebay, some may not. A lot of ponds, you're going to have a significant travel distance from the inlet to the outlet. And so you've got some settling that takes place with that. So if we had set this up as a full pond model and gotten whatever results, it would be hard to know what percentage of that was the other items in the pond, what percentage was our filter and skimmer. So we did a worst case scenario. We had this on the right here is the sediment laden water coming into the basin. This is our outer filter. Again, it's just a polyethylene screen. This is our inner filter, the adsorbent, and there's our skimmer. So the skimmer is just pulling water, through those filters. Again, the test tank was about 4 feet deep, had a maximum elevation when we're testing about 3.5, maybe 3 foot 9 inches or so. So the filter was just getting off the bottom of the pond and water coming below there, which would be very similar to what you would have in most cases for a first flush volume. You're typically only going to have 2 or 3 feet of depth in most ponds when you're doing that first flush water quality. And so we did all that, and we got that 90%. We've now developed a commercial version of this, ready to go to market, and put it back in that same pond. So we're testing this again. We've got a time-lapse camera set up on this pond, so we monitor this. We had some really interesting pictures when Hurricane Helene came through. One thing, and I need to add it to our presentation here, this pond unfortunately has been invaded by some beavers. The owner needs to go do some maintenance on this thing because the beavers are doing, but they built a pretty good dam around this outlet structure and has kind of gone over our pipe. However, the skimmer continues to work. It's floating up. The dam's not holding the skimmer down, and it's still doing a really good job of draining the pond. And you can see how much junk is in this pond. One thing about this area, it's about a 40-acre watershed, really old commercial development, and very little stormwater management on the other parts of the watershed. So this is really the only pond in the area. So it gets a lot of junk and debris and pollution off of the shopping centers, and there's a substation up in front of us, and a lot of commercial development. So really good test site for us to use as a prototype. If it works here, we're pretty confident it's going to work in most places. So let's talk about why you would want to consider this. So first, let's just look at a benefit to using filtration method versus a settlement method for your first flush or for water quality. So number one is the peak rate of discharge can be based on the filter treatment flow rate up to whatever first quantity storm event is or whatever storm event's handled by the filter. So what we're saying is first flush method, typically you're holding that 1 inch or 1.5 inch volume for 24 to 48 hours. Well, that inflates the volume of your pond to do that. If you can let that water out faster, up to whatever that first quantity control event, which is typically your 2-year storm, you reduce the size of your pond. The other thing with that is the filter treats 100% of the runoff from storms up to the peak rate of whatever the filter is designed to handle. So again, if you design that filter to handle, say, up to that 2-year storm event, what happens when you get a small storm? Our accepted methodology that we use currently doesn't really account for that 1/4 inch of rain over 8 hours, right? You're going to still get enough rain to kind of wash off the parking lot, wash off the pollutants, but it's just trickling into the pond and trickling out of the pond. And if all of our pond water quality is based on ponding to generate settlement, and there's no ponding, i.e., no settlement. So very little treatment. But if it's got to go through the filter, we're going to treat those small storm events too. And then finally, your filter media can be customized to target specific pollutants of concern. And so we've already built in a media that will absorb hydrocarbons and has some benefit for metals. We're looking into phosphorus. I know I'm not sure how many of you on here today are going to be like me and heading to Virginia for the IECA conference. I will be there tonight and rest of this week. But Virginia focuses on phosphorus, not TSS. So most of their water quality standards are based on a TP standard, not a TSS standard. So we're looking into, is there media that we could add, that would help with that. So now if you combine a filter with a skimmer, what you can do is you can use that skimmer to control the peak rate for your lower storm events, right? It's kind of hard to control flow rate through a filter, but that skimmer is going to control the flow rate. The skimmer is going to increase the filter efficiency because it's going to withdraw from near the surface where the water is cleaner. So your filter is not having to clean the really dirty stuff at the bottom of the pond. It's able to filter the stuff higher in the pond. And it's going to make it easier to access or pull to the side of the pond for maintenance and changing. That's not a perfect situation. There's going to be some challenges. So number one, your filters are prone to clog over time and will require maintenance and periodic cleaning or changing. So we have prototyped both versions of ours. The original prototype was in there for 2 years. The new prototype's been in there for about 1 year and 3 months now. So we're going to keep it in there basically probably for 3 to 5 years to see how long it takes before it really starts, having issues. We haven't had to clean it. Still working well. Number two here is the skimmer's got to be durable and last more than a few years to be suitable for permanent use. So you really don't want to use standard Schedule 40 PVC, right? PVC is not UV resistant. It's going to degrade pretty quickly in the sunlight, tend to crack or get brittle. So our product's an HDPE product, polyethylene product. So much more UV resistant, much more durable, suitable for permanent use. Need something with at least a 20-year life for that. And then the biggest one here, and this is really kind of goes out to our MS4 attendees today. There are no established standards or basis of design and permitting when you combine a pond and filtration. Now, there's some standards out there for MTDs or mechanical treatment devices or proprietary devices. And you can sort of combine that with standards for a pond and put them together. In Georgia, a dry detention pond by itself does not meet water quality standards. You've got to do a pond plus something. Well, we've gotten Georgia to say, hey, we're not sure we're going to give you 90% on your filter like you claim to have because it's ASTM and we want to see some more stuff go on, but we'll give you 50%. Well, if you combine 50% plus what your standard dry pond gets, you get to 80% trapping, which is what you're trying to meet. Same thing in Tennessee. That's kind of a similar situation, and we're working with other states and MS4s to see where we can, get approval for use of this. So I will say we're also in the process of trying to get NJCAT approval. That's another step beyond our ASTM approval, but we're working on that. Hopefully we'll have that this summer. So finishing up on this, we're going to go through a quick post-construction water quality model. So kind of go through a volume-based first flush over, I apologize, here my dog's barking, my wife's coming home. We're going to go through a volume-based first flush, release that over 24 to 48 hours, and we'll go to a filtration-based flow rate of filter. So our sample site is going to be 5 acres. We'll have a pre-development condition of 55 CN for a wooded site. Post-development, we're assuming we're going to commercial little shopping centers. We're going to 92. So our pre-development flow rates, based upon a 5 acre wooded site with a time of concentration of 48 minutes, pre-development flow rate would be 0.72 CFS for a 2-year storm, 3 for 10-year, 5.4, and 10.7. We're really just going to focus on 2-year storm and below for this. The rest of these larger storms are going to be controlled by your typical outlet structure. So next step is let's look at our water quality volume and our post-development flow rates. So based upon a 5 acre commercial site, we assumed time of concentration of 10 minutes. So we calculated the post-development flow rates. For a water quality storm, in this case, for our sample, we did 1 inch of runoff. It varies. I just happen to have it here. It's 1.2 inches in Georgia. It's 1 inch in Tennessee, and it's 1 or 1.5 in North Carolina. Indiana, I think, is 1.5. Have to look back and see what Texas and Ohio are. But let's just use, for this example, a 1 inch of runoff is going to generate 18,150 cubic feet. Okay. And so we use trial and error, putting in a storm event, and came up with a 1.73 inch 24-hour storm would generate the 18,150 cubic feet of runoff volume. So when we did that, our water quality flow rate post-development 7.2 CFS, our 2 years 19.72, and you can see our 10, 25, and 50 and 100 all jumped up, a lot from pre-development. So most engineers have a tool similar to this. So they use a spreadsheet to help calculate that first flush orifice size. So first we're going to look at traditional design using a first flush method. So we've got a contributing area of 5 acres. Our water quality volume, again, 1 inch over that total for a dry pond, 18,150 cubic feet. We want to maintain the volume for 24 hours. So our average flow rate is 0.21 CFS. We do some calculations based on orifice equation and average head, and voila, we come up with a 2.6 inch orifice is going to release that volume over 24 hours. Well, what are the faults for this? Well, number one, is this volume going to all enter the pond instantaneously? Obviously not. Even if you have the, frog strangling thunderstorm that downpours a couple of inches in 30 minutes, it's still going to come in over some period of time and go out over some period of time. So that's really not accurate to say, hey, this volume is going to get there and flow out. But that's what we use, and that's kind of the standard, so we'll go with that for now. So here's our hypothetical pond. So we've got our water quality volume. Bottom of the pond is at 110. We're saying it's going to take about 3 feet of volume, or 3 feet of depth to generate that volume. So we put in our 3 inch low flow orifice here. I went with 3 inch just because that's what most contractors would put in, because it's harder to make a 2.6. We put in a 3 inch orifice at that top of the water quality volume. That's going to control our 2-year storm. Put in an 8 inch orifice 2 feet above that for a 10-year storm, and then top of the riser controls from 25 and emergency spillways for the 100. So if we run that storm event, we're going to see that our water quality volume releases at 0.25. Again, we were shooting for 0.21, so we're letting out a little bit quicker than 24 hours. We have to tweak that. Peak elevation is 12.5, so it's not getting all the way up to the 13. So we got a half a foot of volume we're not even using here, because the volume that required in the pond is only 10,672 cubic feet, not 18,000 cubic feet. So we've got, 7,500 cubic feet of volume in this pond that we're not utilizing for our detention, because it's built in this water quality volume, even though the water quality is not using it. 2-year storm is going to release at 0.81. If you remember, our pre was 0.72. So we're a little bit above that, less than a tenth. So, depending on the area and what you're doing, they may let you do that. Our 10-year and 25-year are being detained. So now if we said, hey, let's look at the option of doing it with a skimmer, what skimmer would we use? So we're shooting for that 0.72. So a 6 inch skimmer with a 6 inch orifice has a peak flow rate This peak flow rate in this chart is based on a 4-foot depth, so it's going to be a little less than that at a 3-foot or 2.5-foot depth. So let's try the 0.78 CFS, peak rate skimmer in here. And then this is the detail for the filter. So a couple things to point out about this. We list out a outer and inner L1 and L2. The reason we have that is because this length and this length may not be the same on all the filters. Some of these filters, in order to meet the criteria set by our testing, get pretty large. So what we've done is we've designed the filter to, based on our testing, we determine what the flow rate per square foot of filter could be, and we determine what the flow rate per linear foot of filter. So let's assume all the water goes through the filter. What's the max flow rate for that? Let's assume the filter is 100% clogged and all the water went under it. What's the max flow rate of that? And so we kept those ratios based on the testing of our 4-inch skimmer, and we applied that to our 6, our 8, and what we call our max 8, which has a flow rate of just under 2 CFS. So based on those criteria, some of these L1s and L2s, get a pretty big difference between them. So like our max 8, the outer skirt here, L2 is 16 feet, L1 is 46 feet. The reason we do that is we don't want this over 16, because we typically don't want this pipe to be over 20 feet, because then you have to start joining pipes together and those joints create issues. And as this skimmer rises in the pond and gets up to a 45-degree angle, it's going to get closer to the outlet structure, right? So you're going to have this come within, if this is 20 feet, it's going to get within about 10. And so we've got about 8 feet of distance from here to here. So we don't really want the filter hitting the outlet structure if we can help it. So that's why this is limited to 16 feet. And so therefore we have to go whatever length we need to go to get that total area and total length for the filter. Then we have our standard detail here. Some of you may recall our previous details showed the skimmer parallel to the dam. We did that for ease of maintenance and just being able to check it. In this case, because these filters can get pretty large, you need to pay attention to where they are in the pond and make sure they've got room and they're not getting stuck on a bank or side or something. So just something to be aware of. And you may have a permanent volume in the pond. You may not. There may be a dry pond, maybe a permanent pool in here. But you got all your standard information again, similar to our previous detail. So now let's look at the hydrology if you run that way. So we're going to model our 6-inch skimmer instead of a 3-inch orifice. And so what happens is your water quality volume is now getting released at 0.7 CFS. If you recall before, it was 0.25. So we're letting the water out nearly 3 times as fast. Because of that, we're only using 7,600 cubic feet of volume in the pond. So it's only getting up to an elevation of 12, or 112 actually. So it's 2 feet deep here instead of the 2.5 that we had, or the 3 feet that's required by the volume. Our 2-year storm is letting out at 0.78 CFS. So we got it a little bit closer to that 0.72. But the main thing here is the skimmer is handling the 2-year storm event. So because of that, since we got the filter in here, every storm up to that 2-year storm is getting treated. 100% of the water is having to go through the filter skimmer combination. So, because so you're now treating much more of the annual rainfall, not just that 1.73-inch storm for water quality. I think the 2-year storm I used was around 4 inches of rain. So a much larger rainfall is being handled now by the skimmer and filter. So if we compare that, actually I'm going to skip that slide. It's a little hard to read. This one's a little better. So the difference in storage required for the traditional versus the skimmer, it's almost 30% for your water quality pond and 14 and 12% for your other storms. So your pond got smaller. Go to the summary here. So skimmers are less prone to clog, because you don't have the outlet above pond, and require less maintenance to keep the pond functioning properly. Again, ponds are designed to capture sediment and for the sediment to settle. It's settling to the bottom and it's going to cover whatever that low flow orifice is over time. So you're going to need more maintenance. If you use the skimmer, you're releasing from the surface, and so it'll continue to function better. Skimmers can be a very effective way to retrofit existing basins. I didn't mention that before. Do want to mention that now. This is a great way if you're redeveloping a site and that site has a pond, but the pond was not designed for water quality. Let's say that pond's 30 years old, right? We didn't do water quality for the most part back then. Some areas we didn't do water quality in the last few years, and it's just coming around. So you've got a site, got a pond in place, but you don't have room in the pond to go in and hold that first flush volume because the pond would have to get bigger. If you can put the skimmer and filter in and maintain that 2-year flow rate, well, now your pond size stays the same and you've just provided treatment for the entire site to 90% TSS. So great way for retrofit of basins. And then again, the surface draw releases cleaner water for the basin. Again, our skimmer has been third-party tested to confirm 90% TSS removal. It treats more than annual rainfall. Again, treats the very small storms up to the larger events, and it reduces your pond size. So I've only had one engineer so far tell me that their client wanted a bigger pond, and that was in a coastal area, and they needed the dirt. So they were digging the pond bigger and deeper because they needed dirt for the site. But pretty much everywhere else, they'd love to have smaller ponds on their sites. So we'll wrap up here. Last poll question is for those of you that were maybe on the no or maybe, now that you're aware of the benefits, would you consider a skimmer for permanent use? And I do want to qualify this. If you're in an area that has frozen conditions, you're gonna need to have that alternate outlet in there because you're gonna have to account for that in some days. So we're about out of time, so I'm gonna do a quick poll, but about half of you said yes, and others maybe had a couple of no's, and understand that. Usually I get a couple of no's each time, which is fine. You're the engineer of record or the MS4, so you get to decide in your area. Run through here real quick. This is our website. We've just done some updates on it. We always keep our webinars on there. So this is being recorded, so it'll get uploaded. We also have a training series, so it breaks it down into small bites, 10, 15-minute segments, focusing on a topic. So please check those out if you need to. This is our engineers pack. So if you go to our design spec cut sheet page, you download this. It's a zip file. It's going to give you your details, the Marley float details, test data, design tools, give sediment basin details, and water quality basin details. It'll put those in 3 different folders and organize it for you. This is about our skimmer. So it is made of HDPE pipe. Again, has this debris guard around it, so water has to come below that debris guard. We say it works in mild frozen conditions. So if you get a foot of ice, it's not going to continue to work. But if you get 2 or 3 inches of ice, it will still work. This is our orifice plate. Talked about it earlier, so just wanted to show a quick video here how you take it out. It's got this little metal nub here. Make sure that the orifice is always centered on the outlet so it works well. Every model is going to have anywhere from 3 to 5 flow rates in each device, so it's going to have a wide range of flows, and they're all third-party tested to verify the flow rates. We redesigned our skimmer about 5 years ago, 6 years ago now. The original version had some weight on the top, and it would kind of lean. This version always stays level. So, hopefully nobody's ever out the pond moving around like that. But if they do, it comes back to where it's supposed to be. Our 6 and 8-inch models are pretty heavy. They weigh about 200 pounds because they've got to counteract the buoyancy of the pipe, but they have handles on them to make it easier. And this is our flow rate charts. We have 6 different versions. One thing to point out is we have 2 different 8-inch versions. So our standard 8-inch uses a 6-inch pipe. With our 8-inch pipe, we call it our 8-inch max, uses an 8-inch pipe. The reason we did that is because the 6-inch pipe or 8-inch pipe are below the water surface, and once they start flowing and get a 45-degree angle, there's a lot of buoyancy there. So it allows us to weight the 8-inch less, and we still got a much higher flow rate. Most of our competitors are around 1 CFS flow rate at an 8-inch, and we're at 1.5, so much higher flow rate there. Real quick, I'll show you our VersaWaddle. So this is designed to go down mainly places that have curb in and asphalt, but not the final asphalt surface. So typically water is flowing down the road and not getting into the box. So this goes down, so traps some sediment, kicks the water over the curb in the box. And the big thing about them is they're designed to be driven over. So they can do have vehicle traffic or even have a dump truck drive over them. And there's not many other products out there that can handle that. So if you need inlet protection, especially on subdivisions that don't have final surface, good product to have there. Also, if you've got inlet in a shopping center, like in the middle of a parking lot, it's hard to provide sediment protection there. You can either use some kind of bag underneath it. In this case, we're trying to keep the sediment up top to keep it clean, or in a sag here. So that's it. Appreciate everybody staying on. Sorry, we went about 5 minutes over, but if you would like a PDH certificate, please email us. Send that to info@rymarwaterworks.com, and we'll get you a certificate out. Those of you in Indiana, we are approved now in Indiana to provide PDHs, so we're officially approved there. Most other states don't have an approval process. If you're in a state that does, let us know. We're happy to go through that process. We do keep this very technical, and hopefully you learn something. But if we can be a resource for you, please let me know, and hope you got something out of today. I don't think there's any questions in the chat, or if they have, I think Lynn has actually answered most of them. But if anybody has any questions, I'll be glad to stay on for a second. Or if not, if you need to get on with your day, I understand and appreciate you joining.